So, well, start with, thank you for the invitation to come here. It's always a pleasure to be in Madrid and to share time with all of you. Um, as you know, I don't know anything about the Swampland, so and I'm not working that much on that. So, in that sense, I will just show my ignorance by asking questions that I think will be interesting to address, and maybe some of the Swampland experts they have some answers to that or some opinion or something, just to motivate the discussion. And then Gary would play the role of the good guy. Okay, and so I see this as like at the end we're looking for something realistic coming from string theory, and we know that we have the very limited resources because we don't have experimental predictions that can be tested in a short term, and we are all in this together. In that sense, we are all in this together, and we are sympathizing with the people searching for a needle in the haystack. That we are just kind of lost, and then but it makes sense to organize our thoughts and try to do something. And so we have several approaches for the needle in the haystack. One is a brute force. The other one is a top-down. Just look from a magnifying glass and see if you can find the needle. The other one I like, which is the bottom-up. I also you just put a magnet and find a needle. And the Swampland, when you can have here the needle, you can say the needle is not here. So, and I think we're all in this together. So I think it's worth exploring all the different techniques, and I think we should learn from this. In that sense, that is good. But essentially, the challenge is very high, so we have to use as much as possible all our resources. And I find the Swampland as one of the ways to do it, which I think is very good. Okay, so what I would like to do is to show some things and ask some questions. Probably at the very end, I summarize with a list of questions, but just to see what is it that we want to learn, hopefully with the cosmology from the Swampland. And of course, before string theory, people had done quantum cosmology using mostly some classical gravity. So I can start with that. This is there are open questions: the origin of space-time, the Big Bang, or there's something before, the source of density perturbations, which most probably they are quantum in nature, the issues of naturalness that become worse and worse because of the dark energy, acceleration of the universe, and we cannot forget that we're not talking only about gravity, but it has to be the whole standard model. So we can decouple gravity when we talk about the standard model, but otherwise it's not clear. We can decouple the standard model when we talk about gravity. So, and people have tried. For instance, there's the famous wave function of the universe with the Wheeler-DeWitt equation, and the work of Vilenkin and Hartle-Hawking about the creation of the universe out of nothing, and with the Euclidean picture having imaginary time here, and then at some point have the expansion of the universe with the Lorentzian, just as a technique of doing the calculations. This can be seen as a potential for the scalar field, where the scalar is the scale factor, and with a long kinetic term. So this looks like a barrier, and so the barrier passing through the barrier is like a turning from nothing to something, and then create the universe. All those things I read many years ago, and I never paid that much attention to it because I found that was too much of a speculation without knowing a real theory of gravity. Well, it's good to see that these people have been pioneers in the field, and I think it has to be taken seriously. One of the reasons that I find is that recently with this progress made about the black hole information loss, they also use this kind of semi-classical gravity, and got very far. So in that sense, maybe we should take these ideas more seriously than before. And a similar fashion is the vacuum transition that Coleman started. And it's interesting that I was realizing recently that this predated the Hawking, Hartle, and the Vilenkin. So the transition from one vacuum to another is again semi-classical gravity. Yes, because it's a quantum phenomenon in gravity, and again is mostly using the Euclidean approach. We have been working on the Lorentzian approach, and it's extremely limited. So the Euclidean, I can see why it is the most common one. But I think a similar approach has been done by Brandon Tatebaum, where you can talk about a bubble nucleation directly. So in that sense, there's not necessarily you can go from fluxes to another fluxes here without a potential going from here to here. So this will be the Coleman-Delucci, and it will be something like Brown-Tatebaum would nucleate the bubble. And there's this Hamiltonian approach that Fisher, Morgan, and Pociński pioneered. And then they have, as I said, they don't have a potential. You have one vacuum with a cosmological constant and another vacuum with another cosmological constant. But this one is more trustable, I would say, because it's Lorentzian directly, but it's very limited because you cannot do it for the cases that they do. But I think it's still interesting to consider. Then and I insist, this is another area beyond the black hole that most people have been working on, where gravity and quantum mechanics are important. And for string theory in general, I welcome this invitation because I was invited by my colleagues to write a physics report that we are writing at the moment with Michele Ciccoli, Joe Conlon, and Sean Magaran, and Susha Paramasobaran, and Yvonne Zavala. And so in that sense, it is helping me to come here. I confess that I volunteered to write the Swamp part. So, wish me luck. So, and so it's good to see that when we talk about string cosmology, most of the time we only say about the string inflation and this kind of things, but people have been discussing many ideas which are very nice and show that there are things that to be done, the original work of Brandenberger and Waffa, which I always found fascinating, realizing that T-duality can play an important role by defining how you define the spatial coordinates in one regime or in the other regime, the duality, and also the fact that you can have in string theory you have the high-down temperature as a limit temperature where we will expect to have a phase transition there, and I think it would be interesting if we can say something about that, or we can incorporate in our model of the high-down temperature. I know that some people here, I think Ralph and others have been working on that recently, but it would be nice to hear if there's something new that we can say about this phenomenon. The pre-Big Bang cosmology of Veneziano and Gasperini, again, they were using the same ideas of duality, but just for the scale factor duality, combined with time going to minus time. And of course, they have some cosmology, which is different from inflation, but of course, with the big question mark in the Big Bang part, and the one from for t equal to 0, from minus t to 3. The ekpyrotic that was very famous for some time, combined with cyclic. It started very much motivated by string effects, with some it's kind of end of the world brains moving towards each other or something, some moving brain frames in the middle. Then they changed it several times to face some of the problems. And at the end, I think they have potential like this, where you can have a rolling field and going back, and then they become cyclic. But the more complicated this potential became, the less stringy it became. But it's interesting to also think about that. Then there's the bubble of nothing that we then found in the again in the early 80s in Gauss-Klein, but then can be extended directly to strings. I think that's an interesting thing that can play an important role in cosmology, in the sense that at some point you have a transition, say, from something to nothing. So and contrary to the Vilenkin and Hartle-Hawking, there was from nothing to something, and apparently the two nothings may be the same. And this was the first time nothing was used, I think. And so I think it's a question to see how much we can say about that in string theory. And I know people here also have worked on that, and I will motivate them to say something. I think Miguel Levin and collaborators found that this is very generic in string theory, which I find very interesting. The famous ace brains, the rolling tachyons. Again, there are interesting cosmology from string theory. Similar to the other effects, like this one, that one, and that one, and this one, they all have a period of contracting universe before expanding. So I think it's interesting to take them into account. Here, it looks the Penrose diagram, which is the pi/2 rotation of the Schwarzschild one. Then the interpretation, you have a contracting universe and an expanding universe. And this is very closely related to the idea of the rolling tachyons that Sen also was able to compute the potential as well, and study the cosmology, Gary Gibbons also, and others. And this had a nice interpretation for the open string to be when you have brane inflation, brane anti-brane inflation. At the end result of the brane anti-brane inflation was through tachyon condensation, and then the condensing the tachyon was the disappearing of the branes, which I find also very exciting. For the closed string tachyons, much less is known, but I think again Swampland conjectures have been used, in particular the coverdism conjecture, I think. And I think there are people in the audience that have done something. I was expecting to see Angel here, but I don't see him, but probably some of his collaborators may say something. And for then string inflation, that has been probably the one that has attracted much attention. And we have several models of string inflation, which it makes sense for several reasons. One is because once you make contact with inflation, then you know all the success story about inflation can be adapted. And so just trying to find a model that gives you inflation is very good. And in the first decade of this century, there was several models of string motivated inflation came, like the brane anti-brane inflation and so on. And this is a table that I think probably we will revise in this review I'm telling you. But let's capture some of the predictions for NSR. And some of these models are already ruled out. I think I confess this one, which is from us, NS is not very good. And and some others can be tested soon because of the R is relatively large and so on. So that's something to keep always in mind. There are some models of inflation, not too many. I think there are less models of inflation than some conjectures. So in that sense, and then they can be tested and ruled out, and some of them can be improved. They are not perfect. They have some issues. Some of them either problems or different scales. So some of them still don't have model stabilization realization, and also confrontation with experiments. And then also there is physics also after inflation. So string theory can tell you something before inflation, like vacuum transitions or creation out of nothing, then inflation, but also the physics after inflation, which is not trivial, because inflation, you have people is famous for erasing everything that happened before, but the model being light survive inflation. So in that sense, that's something I think is very interesting, that we can talk about cosmology even after inflation. And there's something very stringy, because the moduli are the fields that determine the shape of the extra dimensions and the size. And they can be the source of reheating. Instead, at the end of inflation, it is the model fields that actually reheats in the universe and not the inflaton, for instance. Or there can be several regimes, like this one will be like oscillating about the minimum. That will be like matter domination, similar to the axion physics. Or it can be something like that a long run from the inflation to today. So that could be large scale inflation to low scale real world. And this running will be a long region field space, something that can be contrasted with conjectures and so on. And this has nice features that Conlon and collaborators have been pushing for recently, because of the combining high scales with of cosmology with low scale of the real world. Also, these fields give you naturally this non-topological objects like oscillons, oscillatons, cuboids, and so on, or boson stars that can have nice implications for observations in gravitational waves and so on. Also, dark radiation, which is one of the killers of any model building, because we have many hidden sectors, and we already know that delta NF is almost 3, and we wouldn't have that much room for more radiation than neutrinos. So that's a big constraint thing for string cosmology, and it would be nice if people with experts on the Swampland conjectures can say something. And by the X-Sieverts, we hear now that nice talk by Matt and others. So in that sense, that there's things to be done. Okay, so and then for the Swampland, I will say some mostly questions. There's, the distance conjecture will constrain large field inflation. The de Sitter conjecture is against de Sitter. Transplant here also to some constraint. And the cobordism, I have to confess, I have some weakness about this one. I like that one. I don't like too much this one. And one of the reasons I don't like that much the Sitter, because I think it's correct. People have been saying now today, I pay attention to the wording. Asymptotic has been embedded into the claims, and this is correct. So asymptotically, we all know that I say DS means dying cyber, and and we know that has been the rolling vacuum is a natural thing to have. And the question we are after is there are non-trivial minima. Ideally, in this regime where you can still have weak coupling or large volume, and in this regime, we all know it's complicated to have something on the full control. It's essentially impossible. The full control will always be here. So in that sense, a lot of work has to be done here. And I have to say, the conjectures already has made an impact on this because it has revived this story about the modular stabilization that was popular in the early 2000s. It was less popular after that, because people got exhausted or just tired. But now, since people from the Swampland are questioning the Sitter, it has forced people working on getting vacuum like a KLT or LBS to improve in their control of the calculations. So in that sense, I see that as positive progress. And of course, even this regime, this conjecture holds this. But I mean, there's a minimum people will expect to be in this regime, but in this regime we don't have hierarchies, so that's what this regime is. This is, I would say, is preferred. So any discussion or opinions about this, I will welcome. So something I would like to emphasize, alternative to the Sitter is quintessence, and I want to emphasize that I think Irene said it today. I think which is very important to say, because in the past we had this strong discussions about that runaway is very generic, but runaway is not quintessence, and we have seen today in several talks that this is not a straight forward. In particular, that Irene's and Tom's talks, which are very precisely on this point, that quintessence is not a natural thing to happen within the stream solutions. It's not that runaway is natural, but quintessence is not. And I had in one of the stream phenomenology meetings, I had my own conjectures. I had two. One is that if the Sitter is part of the swampland, so it should be quintessence, because it's equally difficult or more to get quintessence than the Sitter. As you can see from Irene's talk, for instance, you can talk about rolling scalars, but at some point you need to stabilize the other direction. So you need to do all the work that we have been doing for stabilizing of the modeler. My other conjecture, I say that public, is that the standard model should be in the swampland, which is that I like very much, because that will motivate for something beyond the standard model. But of course, it's just words. And anyway, so I finished with some questions. Can we say something about the wave function of the universe from string theory in general, or from swampland? I will welcome some comments from you. The same thing about vacuum transitions, what happened to the Sitter to the Sitters, and so on. If you can have, after all this year, because swampland is not a new subject that we have been working for 6 years, so now we have to question what is the progress in the field. Is there a new idea about inflation? All the models of inflation that I mentioned were more than 10 years ago. If not, is there any preferred class of models that is beyond inflation? That's other question. So you prefer something else, like the, I don't know, the pyrotic or cyclic or something, for some reason of properties of this swampland. Any ideas about what reheating is? If we can still incorporate the model as reheating, or someone can tell us something. Alternatives to inflation, as I said, all these questions the same thing. Can you say something again in favor or against any of the ideas of alternatives to inflation that I mentioned before from the swampland? I know some of the swampland conjectures say things against inflation, but can they say something in favor or against the other proposals, or come up with a new proposal? The other thing which I find is more relevant is the alternative to the landscape to address the dark energy. I always say that the landscape, the Weinberg-Busse-Polchinski approach implemented, if you have the model stabilization under control. I always say that it is the worst solution to the cosmological constant problem, with the exception of all the other ones. So if people can actually come up with the new ideas, I think that will be welcome. The same thing about quintessence. Dark matter candidates, I think we heard now talks today. I think Dieter and Miguel and company, they have ideas, which I think are very welcome. I haven't heard that much about that radiation, but I'll be wrong. Have any comments on the radiation? And don't forget that the standard model should be also taken into account. That I always say getting inflation without having the standard model is, what is the point? You have to have something very close to the standard model, at least a chance to have something, a chiral sector with the gauge fields and so on there, that where you can get some cosmology to work. And I think for that, I have seen the papers of recent collaborators about neutrino masses or something that could be in that direction. But anyway, so I welcome all of you to say some comments or opinions about any of these questions and any other ones that I haven't thought. Okay, I stop here. Thank you.
Okay, so I think we go with Gary and then we
Yes.
start with the question. There are already some in the chat, but we can wait a little bit.
All right, so can you hear me well? So thank you for having me here. It's always a pleasure coming back to Madrid. The organizers asked Fernando and I to lead a discussion on Cosmo and Swamp and endowed us with the title of Swamp Stirrers. I wasn't sure what the organizers meant and how they would like us to stir Cosmo and Swamp. So I did what kids nowadays like to do. I asked AI for help. So apparently, Cosmo and Swamp is a drink, and this explains why this discussion is scheduled right before the reception. How to do this? Or maybe I can just do it here. No, it doesn't help either. All right, so personally, I think it's important to have an open discussion on this topic because many feel that the pendulum has swung too far. And this sentiment is shared by both sides of the aisle. So it was perhaps too hasty to accept that there are 10 to the 500 de Sitter vacua. But others may say the same about having none. The truth may be somewhere in between. But if the number of de Sitter vacua is not in the 10 to the hundreds, then arguments using anthropic reasonings in explaining the smallness of the cosmological constant would not hold up. Now, only after we establish what kind of vacuum do we live in can we address the next level question of whether inflation is realized in string theory and whether a detectable level of gravitational waves can be generated by inflation in a consistent quantum theory of gravity, as well as all the nice cosmological issues that Fernando brought up. Now, since these questions are rank order, I would focus on the top level questions today. And if I understand what the organizers had in mind, the job of mine and Fernando's is to put de Sitter on trial. And just like any fair trial, we will try to present different sides of the arguments. Now, given time limitations, I will not be able to mention every argument either for or against de Sitter, but if you feel that your work was not featured, you have an opportunity to bring your work to the spotlight during the open discussion. Now, a viewpoint that you sometimes hear people express is we are too harsh on de Sitter. The argument usually goes as follows. Nobody has ever constructed a modularized, stabilized string vacuum containing the standard model. Why are we so critical about de Sitter vacuum in string theory? Now, this point was also brought up in the discussions at strings this year. I wasn't there, so I don't know who said this, but I find this type of arguments lacks intelligence. So if somebody says your football team sucks, you don't respond by saying that your basketball team also sucks, as if this could justify the outcome. Instead, we should look at the positive lessons and try to understand why it is difficult to find controlled de Sitter vacuum. Now, we also need a fair baseline for comparison. So George Box famously said, all models are wrong, but some are useful. Now, if you have never heard of him, he was a giant in statistics, often referred to as one of the greatest statistical minds of the 20th century. So a lot of important work on Bayesian inference was due to him. And of course, he was referring to statistical models. But I would like to argue that the same comments apply to string theory models as well. So with incomplete knowledge about the ground truth, the best we can do is to set a threshold for when we can claim that we have it. Okay, so experimentalists do that all the time. This is perhaps less common to theorists. As an example, the famous microstate counting of black hole entropy was done for 5-dimensional black holes, supersymmetric black holes, not black holes in our world. But I think most would agree that it certainly passes the we have it threshold. So what would be an agreeable threshold for claiming that we have a de Sitter vacuum in string theory? Now, since people brought it up, we could contrast this with the program of getting particle physics from string theory. And I will start with a wish list, which I hope you would find reasonable. Of course, you can disagree, and this is what this discussion is about. You could express your view during the open discussion. So I call this a wish list, but you should really think of it as a priority list, because if we don't limit the wishes, eventually the two lists would converge, because particle physics and cosmology are not separable in the string vacuum. So think of this as my priority list. So I would start with the requirement that all moduli are stabilized. At least all the geometrical moduli are stabilized. Now, this is usually not a top priority for string phenomenologists in building particle physics model, but I think it's fair to make it a common denominator. One cannot claim that particle physics model builders have an unfair advantage because we start building particle physics models decades earlier. So this sets time 0 for both research programs to be the beginning of this century, a few years after we have observational evidence for dark energy. Now, to me, a reasonable next step after stabilizing moduli is to incorporate non-abelian gauge groups, chiral fermions, and the Higgs mechanism in the model. A comparable as is a stabilized vacuum with possible positive cosmological constant in some dimension d, not necessarily 4, but where the gravity is dynamical. Now, if we manage to do all that, we can begin to address the next level of questions of whether we can construct models, whether non-abelian gauge groups contain SU3 cross SU2 cross U1, the chiral spectrum contains the standard model, and there are no chiral exotics. And it would seem fair in comparison to ask for a de Sitter vacuum with an exponentially small cosmological constant. Again, not a realistic value, but a way to generate exponentially small positive CC solutions. Now, if we if all these criteria are met, we can begin, at least on the particle physics side, to get the masses and the couplings right. This is usually the step which fails. There are a lot of numbers to match, just a handful of them. If they don't match with what we know, the models are no longer viable phenomenologically. And it would seem more than fair in comparison to us in the de Sitter model building to just get one number right. Okay. So how far along are we in these endeavors? On the particle physics side, we have gone quite far. Not long after we know how to stabilize moduli, Fernando and I already find MSSM like solutions with almost all moduli stabilized. We couldn't quite stabilize all the moduli if we insist on a Minkowskian vacuum. So a year later, Paulo, Ana Maria, and Luis show that they can do much better with ADS vacuum. They construct MSSM-like ADS vacuum with intersecting D6 branes and establish that all the closed-ring moduli are stabilized. Now, they're referring to these models as MSSM-like and not MSSM because the number of Higgs doublets is more than minimal. But other than aesthetics, there's nothing wrong phenomenologically having more Higgs doublets in the spectrum. Now, there are also additional matter fields that are charged under the standard model, but they can be made massive and integrated out when the hidden sector branes recombine corresponding to turning on open string VEF. So if we were to set our threshold somewhere here, I think we can say fair and square that we have it. Now, the response time from knowing how to stabilize moduli to getting fully explicit models is about 3 or 4 years. So we can contrast this with the search for de Sitter vacuum in string theory. And in the same setup, namely type 2A string theory with fluxes, one can show that with only NSNS Ramon flux, D6 branes and oriented for 6 planes, you cannot construct de Sitter vacuum or inflation. This is, of course, not the end of this, not the end of the world. We haven't quite exhausted all the tools in our toolbox. And it was also pointed out immediately in this paper that extra ingredients such as NS5 branes, geometric or non-geometric fluxes may evade the assumptions that went into this no-go. So it took several years and the work of many people, some in the audience, to establish a set of refined no-go theorems in this context. So the devil seems to be perturbative stability of these solutions, not for reasons anticipated by these authors. Now, a counter argument we oftentimes hear is that the world is complicated. Why do we expect to find de Sitter vacuum without including quantum effects? And Puczynski famously said that one may as well claim that atoms don't exist because they are classically unstable. Well, this may well be true, but this does not undermine the relevance of this work. It would also seem naive for those less thoughtful to justify the lack of these solutions by contrasting the situations with particle physics model building, because as we have seen, we did pass the threshold in that case. Keep in mind that this is also the setup, which claims to have infinitely many controlled ADS vacuum. So another argument in defending de Sitter is to say that the difficulty of control, so you would want to raise your point here, or would you want to wait until?
I can wait if necessary, but it's up to the, I don't know to what extent.
Let's all wait.
Okay. All right. So do bring it up if you have something to say here. All right. So another argument in defending de Sitter is to say that the difficulty of control is no worse for ADS and Minkowski. This difficulty of control, as Fernando reviewed, is known as the Dine-Seiler problem. it can be summarized as the tension between stabilizing moduli and calculability. So a local minimum in the potential can only arise if at least two terms of different orders compete. And it is only a little bit more demanding for de Sitter, which requires three or more different order terms, a balance between three or more different order terms. Now, sometimes you hear people say that their model solved the Dine-Seiberg problem because they managed to engineer the Wilson coefficients of a few operators to get a weak coupling solution. But this is not what the Dine-Seiberg problem is about. If terms of different order compete to give a minimum, why wouldn't higher order terms, including terms that we ignore here, important? Okay, so one way to solve the Dine-Seiberg problem is to have parametric control. But if the number of vectors is finite, as in KKLT or LBS, where the flux choices are limited by Gauss's law constraints, the stabilized value of the coupling, while they may be weak, cannot be parametrically weak. Now, DGKT can potentially evade the Dine-Seiberg problem because one of the fluxes is unbounded. But going from ADS to de Sitter, one finds that parametrically weak coupling still cannot be realized in a stabilized vacuum. So in fact, we gave an explanation why this is expected. So for a positive potential, this exponential fall off is a universal behavior in any field direction at parametrically large distances in field space. And the argument is that unlike Minkowskian or ADS space, for space-time with positive cosmological constant, there is a horizon and an associated entropy bounds. As we go to parametrically large distances in field space, this distance conjecture tells us that there's a tower of states that becomes like and saturate the entropy bound. This dictates the form of the potential asymptotically. Now, this argument is stronger than the Dine-Seiberg argument because it applies to any field direction and not only to the dilaton. It is also stronger than the naive applications of the species bound because the species bound only bound the potential asymptotically and not fixing its form. And this stronger result is often phrased in a weaker form, known as the refined de Sitter conjecture. Now, as Fernando also mentioned, whether this conjecture has any teeth observationally depends on whether we are in the asymptotic regime. Right? On top of it, it also depends the order one constants that appears in the conjecture. Now, the sharpened distance conjecture that Tom talked about this morning can potentially fix this order one constants. But as Tom and Irina also mentioned, there are loopholes. Now, a later proposed transparent censorship conjecture closes some of these loopholes by demanding that subplancking fluctuations remain quantum. They put a bound on the lifetime of de Sitter, and this bound presumably holds not only asymptotically, but also in the interior of the field space. The question is whether we can attribute some meaning to the time scale set by this kind of reasoning. And Lars and I computed the out-of-time order correlators in de Sitter space to establish that de Sitter space, just like black holes, saturates the chaos bound. So this time scale can be identified as the scrambling time, which is the shortest time for a static observer to decode information from the de Sitter horizon. Now, we did not find a breakdown of de Sitter space at that time scale, though Lars and Wasser find in studying JT gravity in de Sitter space that a static observer would unavoidably encounter a singularity at a time scale somewhere between the scrambling time and the page time. And presumably, Lars will talk about it on Wednesday. So at the moment, we don't have bulletproof argument to rule out de Sitter vacuum string theory, but it doesn't mean that we should stop our investigation. So this is what we said in the paper with Hiroshi, Iran, and Kunwon. Let me read the last paragraph to you because we spent so much time going over it when we were writing the paper. And what we said is that we would like to emphasize that not having parametric good control over couplings does not mean that no control is possible. Rather, we view our results as showing that establishing the validity or violations of the de Sitter conjecture will require careful studies of string theory vacua, quantifying corrections, and sharpening estimate of errors in our existing techniques and developing more powerful tools. Given the importance of the dark energy problem, efforts in this direction is well justified. This is the most positive message I have seen said about de Sitter vacua in string theory. So how could this paper be misconstrued as promoting negative energy? No pun intended. Okay, so let me end with a few thoughts along these lines. We sometimes hear people say that if my construction is a small perturbations from one which is trustable, why should there be any problem? Now, I'm going to give a counter argument, not in gravitational theories, but first in quantum field theories without gravity, because the rules there are firmly established. Okay, so to an effective field theorist, the Wilson coefficients of these irrelevant operators, whether you're considering a U1 gauge field or a scalar fields, they are arbitrary numbers. However, a negative coefficient, no matter how small, would violate unitarity and causality. So this is an example that small doesn't mean harmless. Okay? Of course, gravity introduces subtleties. For example, in recent years, it has become known that the positivity bounds could be relaxed a bit in gravitational theories. But these subtleties do not undermine the point that having small parameter does not mean that we are home free. Now let's assume for the moment that having small parameters means control. We should make sure that all couplings are weak and all volumes are large. A chain is only as strong as its weakest link. Now, in practice, this is not always possible, and in which case we would have to have stronger results, stronger results to quantify the corrections. We would need to ideally have exact results for non-holomorphic quantities, which are rare to find. The strongest result I know in this context is the work that I did with Inaki, Hirotaka, and Raffaelli exactly 10 years ago. We managed to compute the Kähler potential for an n equals to 2 compactifications exactly in G string and perturbatively in alpha prime. But this was a rather unusual situations where we can make heavy use of dualities, and continuous effort have been made in quantifying and computing perturbative alpha prime corrections for n equals to 1 vacua. But our understanding is certainly far from complete. But interestingly, some of these n equals to 1 corrections do not inherit from an n equals to 2 parent. Now, in situations where we encounter small volumes, we would have to sum over genuine n equals to 1 corrections to all orders in alpha prime, and not only those that inherit from n equals to 2, because corrections to 0 is not in any ways considered small. So I will stop here and open the floor for discussions. Right.
There you go.
Okay,
That was a
so
question.
any questions, comments? Disagreements? Agree?
There was a question at the back.
I was wondering if in this wish list table that you have, Gary, if on the left side we should put at some point the issue of supersymmetry breaking. Because to me, this is to make a more fair comparison on the two sides. Because on the right, the quest for constructing the sitter automatically breaks supersymmetry, while on the left, it seems to me that you are comparing constructions of MSSM. And I'm not aware of discussion of like soft parameters, terms interior, stuff like that.
Right, that's a fair point. Although I only list things that we know for certain. So we don't know whether there would be supersymmetry or supersymmetry breaking. If you have bottom-up phenomenologists, that may not be something on the table. So what I list was minimally what you expect in a string model with moduli that is stabilized without making assumptions about supersymmetry. Of course, you could put that somewhere in the list, but I would not put it among the top priority because that's not universal.
I was just trying to say that maybe we should try to compare how difficult it is to get the sitter with how difficult it is to get the standard model, not MSSM. Just my personal view.
I have a similar view as yours. I think supersymmetry breaking is very important for the phenomenon. Yes, but that's it.
But as you know, if we just keep going, the list would eventually just be the same. Right? It's a matter of priority. So
More okay, okay. We can have
Yeah, thank you for the presentations, with which I sympathize. I would personally relax quite a lot the wish lists on the sitter side. The first point, even I would disagree because so I think we could do with rolling positive scalar potentials, which means we don't necessarily need to stabilize everybody. Yeah, so to bring up to this, so the Planck constraints on inflation actually now favor an unstable scalar potential when it comes to single field inflation. So unstable is not necessarily bad. When it comes to nowadays, because I think that's more what you had in mind, the present universe, of course, there's the matter of quintessence, which is certainly difficult, but we could also live with something like this, I guess. So yeah, so maybe the requirement would be a not too unstable the sitter or not too unstable potential. That would be my wish list. Regarding the supergravity or classical approach that you mentioned, as you said, it's often well all the time unstable. We're not quite sure why. So maybe this is not so bad. The matter is really about weak coupling, a large volume, and flux quantization, all these things, which is also something you pointed out. But really, the question is on control. So which brings us back to the point by Fernando, where also for classical, we're basically in this region in the middle, or we hope to be in the region in the middle, and there it's basically the difficult one because you're not quite sure about your control. Yeah, but yeah, so that would be the status from my point of view.
so we have questions here, but I don't know how to handle the.
I think we should probably let them speak up.
Sorry?
Okay.
Well, how do we do
Could
it?
we just let him speak up?
Oh, he,
Okay, I have
So
a
please
comment.
go ahead, Kumar.
yes.
Yes, very nice discussion, Fernando and Gary. I'm sorry I cannot be there to discuss this in person, but I just had a few comments. First of all, the idea that the swampland criteria basically tell you where the needle is not there is partly true, but actually it sharpens where it could be, and that actually has led to predictions about our universe. So that's, I think, the positive way of thinking about it, which I think I'll give you examples based on our recent work. In particular, the generalized distance conjecture applied to de Sitter has led to identification of a unique corner of landscape we could be in. It doesn't construct that unique corner. It doesn't tell you how you would get it in string theory, but tell you the other options are out based on observation. So that's very restrictive. So it's not like, it's not just like, oh, it's not there, but actually it points to what it could be, where it could be. And so in paper with Miguel and Irene, we, for example, found that the only possibility with cosmological constant being what it is, if you assume dark energy in our universe is given as satisfying the large distance conjecture, a generalized distance conjecture, it leads to the fact that you have one extra dimension of the scale of micron. And that's very specific, very specific. And it could be easily ruled out in these kind of scenarios. Another example of this idea is the recent paper we just put out with Gonzalo, Montero, and Obid, where we actually apply this in the context of cosmology, where we show, again, using de Sitter conjecture, the fact that the lifetime of de Sitter is not more than the Hubble time in the de Sitter leads naturally to solving the coincidence problem in cosmology. That why is the matter radiation equality the same temperature as the dark energy picks up? Again, that used to be explained one way using anthropic principle of Weinberg, but actually we don't need that. So these ideas, I would say that there are circumstantial evidences in our universe. For example, the question of why now is something which would naturally fit with the de Sitter conjecture that the lifetime of de Sitter is perhaps of the order of Hubble, and that would fit in very nicely. So I think the connection between the swampland and observation is a very powerful tool. And I think these are heading in the direction of potentially connecting string theory and quantum gravity to observed universe. So that was my main comment.
Thank you, Conrad. Just just as a comment, the haystack that I took to put on the picture was much bigger. So I just cut it, I just crop it. So in that sense, that's a way of saying that that is not totally arbitrary. So in that sense, yes, definitely I agree with you that the conjecture have they've reduced the power of the haystack. And for the other comments, I think that they're interesting. I have to say that these recent papers about the fifth extra dimension, I like it in the sense that it is much more constructive. So you have a concrete proposal, and the swampland gave you the motivation to do it. Which I think that is what I think it should be the target of many of the initiatives in the landscape. So I definitely welcome it. It is good that you have this coincidence problem approach. But my question to one of you would be, can you provide something, some alternative to the landscape for the cosmological constant, for the natural issue?
Yes, I think that indeed the generalized distance conjecture solves the cosmological constant problem. So let me explain. So that's actually a point that is probably not appreciated. So if you assume the generalized distance conjecture applies to de Sitter, what we are saying is that when lambda goes to 0, there should be a tower of light state whose mass goes like some power of lambda of order 1. If you assume that solves the cosmological constant problem in the following sense. It means lambda itself is m to some power, where m is the light tower. In other words, the cosmological constant does not start from a UV plus a correction. So that already, the generalized distance conjecture is a solution to the cosmological constant problem.
But for instance, what about loops of the standard model particles?
No, those are included. It just implies that. It's the same thing. So in the paper we explained, in the original paper with Miguel and Irene, we explained what is it that's happening in string theory that's different from the effective field theory? Why don't you get the contribution of all the towers contributing? The same thing happens in string perturbation theory, for example. The string tower do not seem to contribute except for the light ones, the stringy modes, to the cosmological constant. Why? In that case, SL2Z cuts it off. Of course, SL2Z of string theory is a very stringy phenomena. It's hard to explain that to an effective field theorist. Why do you do this cutoff? But that was crucial to cut these UV modes off. And the same ideas actually is related to the generalized distance conjecture. So the idea that the distance conjecture may be valid already is a solution to the dark energy problem. The fact that the dark energy is set not by the UV scale, but the IR scale is the main lesson that it tells you.
But so, for instance, you take the effective theory that we say the standard model, compute loops of particles.
Yes.
How would you explain that they are cancelled?
So let me try to explain it in a different way. Suppose you take a string theory even in non-supersymmetric string compactification, even if there's state potential is running and all that. That theory will also have things like D-branes wrapped around cycles, no problem. But then you say, I take G string to be small. If you take G string to be small, and then you say, oh, these are guys are going to be very heavy D-branes, so they're going to contribute in their loop. So therefore, the computation we are doing in string theory is completely meaningless because these are going to be there. On the other hand, string perturbation becomes better and better as G string goes to 0. And it tells you that the corrections that you're computing is of order of string scale to some power. So it shuts it off. In other words, the string perturbation theory already tells you there should be a magical quote unquote cancellation of all these modes that we have. And so from an effective field theories, it looks totally bizarre and unjustified, but it already follows from what we already do in string theory.
Interesting. Well, something that.
Yeah, we have given a few examples of this type in our paper with Miguel and Irene. And I think that the follow-up paper, which just came out this week, gives a very interesting picture of what dark matter is, the question that you asked, Fernando, as being dark gravitons, the basically KK gravitons in this extra dimension. And we actually, magically, it gives you exactly the right scale and so on based on the fact that the temperatures are such that it's consistent with the modes to have decayed by the de Sitter time. So that sets the scale of the initial temperature, which sets the dark matter abundance, which sets the dark matter masses and all that in our universe today. So it seems very restrictive and very predictive. So
interesting. Okay. And just to finish with this, and how do you rule out that model?
Well, very, very easy to potentially rule this out. First of all, people are actually trying to rule this out by experiments, if I may say so. There is a group by Adelberger and collaborators in Vienna who are trying to measure deviations from 1 over r squared, Newtonian gravitational force law. And this is already, they have ruled it out up to 30 micron that there is no deviation. We are predicting that there should be deviation between 0.1 and 10 micron range. So therefore, they are actually, the next round they're doing the experiment beginning now is trying to push it down to 10 micron. So that'll be on the border of the areas where you can rule this model out. So those are very concrete things that we can actually try to do, try to rule this out. There are other kind of things that could potentially be relevant in the astrophysical models. For example, if there are any production of these dark gravitons could be inconsistent with any of the observations like supernova or neutron star heating or cooling, those kind of statements have actually been partly tested in various models and they have passed, these have passed the test, but they could be easily contradicted by observations of such examples. So I think there are very easy rules to rule it out. The thing is that the surprising this hasn't been ruled out yet.
And concrete calculations that you can do either in string theory or effective theory to understand this, the way that string theory cancels the effective theory loops?
No, the statement that you're asking is whether or not generalized distance conjecture is correct. I'm saying that the generalized distance conjecture already implies the solution to Cosmo constant. I didn't claim that I have a proof of generalized distance conjecture, but I'm just saying they are equivalent statements.
Right.
If you assume generalized distance conjecture, you're basically assuming the solution to Cosmo constant. And give examples where this works the way we think it does, but we don't give a general proof that always it has to work.
Okay, very good. Okay, thank you.
Yeah.
More comments from people in the audience or in Zoom?
We have another question or comment from Joseph Pena. I don't know if he wants
Yes.
to rephrase it or read it from the chat.
Maybe we could just let him speak.
Hi. No, it was just mainly a comment about boson stars, because again, there was in Fernando's talk, there was a question that, these models, that they're important for boson stars and, boson stars are good for gravity waves and so on and so forth. I think it's a lot of hype, which comes from a very poor understanding of black hole collapse and black hole formation. Essentially what's happening is that, if you want to, people are saying boson stars are good for replacing black holes. And, if we do LIGO and LISA experiments, we measure something, and then, this may signify the existence of a boson star instead of a black hole. And this is incorrect for two reasons. First of all, in order to construct a boson star, you need a light scalar field. whose mass depends on the black hole you want to replace. So if you want to replace a solar mass black hole, you need one scalar field. If you want to replace a Jupiter mass black hole, you need another scalar field. If you want to replace an Andromeda mass black hole, you need another scalar field. If you want to replace 20 solar mass, you need another one, and so on and so forth. So it's clear that boson stars, there's no way on the planet for them to give you a black hole replacement, because again, you need an infinite tower of massless of light scalar fields, which again, I think they're also incompatible with various swampland arguments. This is number one. And point number two, when you collapse matter to form a black hole, there's an argument by Oppenheimer and Schneider back from 1939 saying that when you collapse matter, you'll form a horizon. And the only way to avoid that is by quantum tunneling. And that only happens when you have a huge amount of entropy. But boson stars are just scalar solutions and they have entropy, they have just one state. So it's impossible for a black hole collapse. You can just show by using this 1939 calculation that, it's impossible to form a boson star by collapsing the normal matter. So that's why, again, they are nice toy models, but again, I think they are used in the gravity wave community, but I think in this community, the standards are a bit higher. So that's all my comment.
Interesting points. Would you mind expanding on how the swampland conjectures will say something against the boson stars?
No, the point is, if you want to build a boson star, so you write your Lagrangian, you need to put an extra field, the one which gives you this oscillatory, this oscillon mode, and the field needs to have a certain mass, because again, if you want to replace a boson, if you want to just build a solution describing a boson star of solar mass, you need to have the light field having some, I forgot, 10 to the minus some big number, 10 to the minus a few EVs. Now, if you want to build another boson star to have the mass of Jupiter, in order to replace Jupiter by a boson star, let's say a Jupiter-sized black hole, then you need another light scalar field, and so on and so forth. So all the black holes in the universe, for all their masses, you need basically for every black hole which exists, if you want to replace each and every one of them by a boson star, you need to have basically an infinite number of scalar fields which are all very light. And I think those are ruled out. I mean, I think.
And will that include action stars, like which and people have been working?
So it's again the same problem. If you want these guys to replace, if you want action stars to replace all the possible black holes which have been measured by LIGO, for example, all the
no, just a question of having the pure existence of these objects, not to be anything.
Yes. So the point is, for a given field, these objects only you need a mass parameter. You have GR, and you need another parameter to put something at the scale of the horizon. And whatever you use, whatever fields and so on you use, it will not have the same size as the black hole. And the reason is very simple. If you increase Newton's constant, the black hole grows. And whatever stuff you put, whatever scalar fields you put in your Lagrangian and so on and so forth, your stuff becomes smaller. Gravity makes things smaller. But on the other hand, the black hole horizon grows. So if you want your blob of stuff, whatever it is, neutron stars, quark stars, grava stars, action stars, everything which everybody and their brother considers, if you want that stuff to replace a black hole, it should grow with G Newton in exactly the same way as the black hole. And you need an ingredient to do that. And in string theory, there's only one mechanism, which is essentially fastballs or microstate geometries, but those use non-perturbative stringy degrees of freedom, which are debrays whose mass becomes lighter with G string and so on and so forth. That's a stringy mechanism and so on. But everybody who does non-string theory replacements of black holes, essentially using some Lagrangian with some perturbative degrees of freedom, it's impossible using these models to get something which replaces the black hole for all possible scales. And you can just go into all these papers and you can just search, all of them, they put some extra light field, they put some extra scale, or the object they built doesn't have the same mass as the black hole and the same size.
Okay, well, it's a strong statement, but it's good to hear what you say.
It's a universal, I mean, it's a very simple feature. I mean, if you just look at, just take any Lagrangian, couple it to gravity, and put some constants there, and just run your calculations, you can see that the size of the object you build, when you make gravity stronger, it will collapse. Gravity is an attractive force. The only thing which becomes bigger when gravity becomes stronger is non-perturbative degrees of freedom, D branes and NS phi branes, which become bigger, which become lighter. So the stuff you make can actually grow. If you don't make your stuff from non-perturbative degrees of freedom, whose mass becomes lighter as gravity becomes stronger, it doesn't work. So if you just write some Lagrangian with some stuff, it will not work. It will just, whatever you build, it will not have the same size as the black hole. Unless you fine tune it by putting an extra field. Then boson stars do exactly that. Boson stars come in with an extra field, and they fine tune it to basically give you the same mass as the black hole, but it only works for one black hole. You need one black hole, one field, another twice bigger black hole, you need another field, and so on. So you need fields for every energy scale, which again is not a good model.
Okay, thank you for the comment.
Sure.
Okay.
Thanks.
More questions? or comments? Dieter.
Yes. Okay, yeah, thank you very much for both of you for your very nice presentations. Actually, I have a question about the table Gary showed about the wish list or the list of important problems. It seems to me that swampland arguments are so far mainly applied to the right-hand side of the table, namely in the context of a de Sitter or the context of inflation. So basically in the context of the evolution of the universe. But so far, swampland arguments are not so much applied on the left-hand side of the table, namely on the particle physics side of the table. And I think this is for me also very important. I think there are, for example, nice papers by the Spanish group where swampland arguments possibly can constrain particle masses like neutrino masses. I think this is very interesting. Or also attempts to explain the hierarchy problem by swampland arguments. And for swampland arguments, you always use some subtle interplay between the UV and the IR. The standard model plays more in the IR. Quantum gravity is more like in the UV. And I think one should also use the swampland or UV-IR mixing, for example, to explain the hierarchy problem. Or a few years ago, we wrote a paper with Aaron about a possible attempt to solve the hierarchy problem by using the scalar weak gravity conjecture, basically. That is my first comment. And the second comment, I think it's very quick. For me, also one of the biggest challenges is to combine the left side of the table with the right side. Often attempts only address the particle physics aspects or the cosmology aspects. And these are kind of two modules that people have, but putting together these two modules is, I think, also a very big challenge.
I completely agree. And I think this is what makes the subject interesting. We could not just talk about particle physics or cosmology separately. We have to put them all together. Right. And regarding the first comment, other than the applications that you mentioned, potentially you could also use swampland constraints to restrict the type of spectrum that you get. At the moment, we have only knowledge about higher dimensions with more supersymmetry, but potentially you can improve the technologies and go down to lower dimensions and with fewer supersymmetries.
I have a comment. So maybe following Dieter's line, actually, I have a comment maybe for this audience in general, because this discussion session is called Cosmo Swamp. And, you know, in general, cosmology offers a lot of, a huge plethora of phenomena. That, I mean, some of them have been mentioned also, I mean, at the end in the last slide, I think, by Fernando. Yeah, my question, I'm very curious about that because I entered this field as PhD student, that there was this mania of, like, you know, constructing the sitter and working on the sitter. But what? Yeah, my question is, why does this community focus like so much on the sitter? I mean, like it's like it seems like to be like an obsession. And I don't understand really why, because after all, like the sitter does not even, I mean, like constructing the sitter would not even solve the cosmological constant problem. So I would like to hear from people that are more expert than me. Why don't, I mean, like, again, cosmology, I think that nowadays like offer like a plethora of events and phenomena where string theory could try to get in contact with observation. But I don't see this effort from our community. And I believe after speaking with a lot of cosmologists, that they really feel that we don't really understand what the problems nowadays are. I don't know. I would like to hear from people that are more expert than me.
Well, if someone asks me what are the top questions at the moment in our field, I will say that what you can see what people are working. One is the information loss. You can see half of the community or more than half of the community are working. It's motivated by an idea of scientists talking, of course, but and then there's the other one. We have dark energy has been such a big thing. And before they discovered the dark energy, the whole idea of naturalness of the cosmological constant is something that hits you in the infrared. It hits you at lowest scales. So something we should be able to explain. And if we understand particle physics or field theory. And so I consider that for me the most important questions. Of course, there are other questions like density perturbations and all those things with Big Bang and so that I mentioned before. But if someone asks me, I would say I would single out those two. So my question to you will be, what would you answer that question? If someone asks you which are the two or one most important question at the moment in our lifetime, for our community, for our generation.
What I meant is that I mean, at the end, you show like a list of problems that we should
Yes.
answer. Yes. And I do not understand why we should focus mainly on the CITR construction
So
instead of like, I don't know,
just-
I mean, like instead of dark matter and dark radiation, I mean, like all the problems
Absolutely.
that we have nowadays, like
No, no,
Hubble tension, SA tension. I mean, like there are like many, because I'm talking because this is like Cosmo Swamp session. I'm just talking about this because this was the title of this discussion session.
No,
So-
I agree. Yes, that's what I came up with the question. I mean, there are many open questions, and which I think we should all keep in mind.
So
I fully agree.
reheating, all the, you
Reheating.
mentioned some of them already.
Exactly.
And there are a lot of,
absolutely.
there are a lot of like points where I believe that our community, let's call it the string community, could try to get in contact with observation. And yes, and since I'm a PhD student, since 2012, the only thing I've been here mostly in the CITR. Yeah.
Okay.
Yeah, I think I
Very
essentially said in my review, that's the zero of all the question. If we don't even that's the vacuum in which we live, then we will not be able to answer the next level questions. I mean, these are rank order questions as far as I am concerned. So I think,
Can I comment on this? Yeah, I think I want to say the exact opposite of Marco. So, and I want to stress this. I cannot understand how we as a community would have an opinion about details in cosmology, which requires, first of all, the existence of an effective field theory. If we cannot compute the sign of vacuum energy, what are we doing? I mean, I'm not going to look at CMB fluctuations if I cannot do the simplest thing. So I would challenge young people to do the following: do something completely non-phenomenological. If you think that we can, talk about inflation in string theory, well, then show me, for instance, how you can get a 7-dimensional solution with positive vacuum energy, which is completely non-phenomenological. Or if you say something else, some detail in cosmology, that means that you, for instance, can have an effective field theory which doesn't see the extra dimension. Show me how to get some vacuum in string theory which is scale separated, because that is necessary to do effective field theory, right? So we cannot go to details, because then we're doing what we don't want to do, and we're doing bottom-up physics.
I don't agree with you, because these are not details. I mean, nowadays, like we have like more than 5 sigma disagreement for the Hubble tension.
No, but
or for example, like
Marco,
dark
you don't
matter
get the
is
point.
not.
People should work on it.
They
get all my money.
No,
I'm saying, you're asking what can we do? I cannot take any person serious who is doing CMB fluctuations if we cannot even answer basic questions about
But I disagree
vacuum
with
energy.
the word details. They are not details. A dark matter is not details. I mean, a reading is not details. I don't think that's details.
But we are string theorists. That means we start from a full-blown quantum gravity and then we go. What you're asking us to do is to forget about that and go and work as good phenomenologists, and they should be there. They should do this. But what can we as a string theorist tell to a phenomenologist if we cannot even compute the sign of vacuum energy? Come on. This is, I think, the what is at stake.
Yes. Luis, please.
Then you mean that when Gelman introduced quarks, I mean, he shouldn't have done it because he didn't understand what was going on, quark confinement, etc., etc. No, physics doesn't work like that. Very often you assume many things, and then with a bit of imagination and certain, of course, rules, you can find out the important things. You don't really need to solve all the fundamental problems before addressing some specific physical question.
That's a good point. Yes, for instance, we still don't understand confinement, and we claim the standard model. Exactly. Yes, good point.
That's the approach we for 20 years.
Sorry? Yeah, go ahead.
But what Luis is saying, what Marco is saying, that's exactly what string phenomenology did for 20 years long.
Yeah.
Okay. And the good thing about the swampland is that we say, let's sort of change this. And as you know, people brave enough, like Umru and Miguel, Irene, okay, they're really trying to go for, phenomenological applications. But I'm just making a point that I cannot see how we even dare to use the word strings and then say we can go to a cosmologist and help that person with a problem on, CMB fluctuations. How can I do that when I cannot even compute the sign of vacuum energy? That's just the point I wanted to make.
No, that's very valid. That's a good point. Yeah. More comments, disagreements, fights?
There are also some comments in the chat. Maybe people
Yes.
through Zoom want to scroll down.
Sorry?
I was just
Okay,
saying, I fully
computer.
agree with Thomas. I fully agree with Thomas that, if we cannot predict basic stuff, it's like, as if, we claim to do university problems and, we haven't finished kindergarten. At this point, we have to be humble and to accept we are not at the level of understanding what's going on. We can barely do predictions. And, it's really, going and writing papers to tell experimentalists to look for, this tilt or the other tilt is really not feasible. I think that's my opinion.
Okay. I don't know, question? Yes, please.
Yeah, one question. Where do you think there could be some progress at some more theoretical level? Yeah, less conjectures, more solid string constructions, learning how to incorporate fluxes on the worldsheet or things like that. I feel that this has been neglected. We learned how to do modular stabilization, putting fluxes with effective potentials or 10 dimensions, and we've been doing that for too long, I think. I think there is time for some theoretical breakthrough.
I fully agree, but I'm not smart enough to come up with the breakthrough in the spot. But yes, I agree. I have to say that it's good to see that the whole community, community as a whole, and see what other people are achieving. And I find that this progress on this page curve and this kind of things that could be something that can eventually play a role in our field that we haven't used yet. That for me is one thing. And the rest is just, fields move at the speed that sometimes we become too impatient because we want results very fast. But we know field theory has been taking many years to develop, and the atomic theory we can count from Democritus to the 20th century is a lot of time. So we're asking big questions, so we have to be patient, I guess, in that sense. But and I think it's good to have a good community here. People are very active and making progress slowly. And the breakthroughs, we would like to have a breakthrough per day, but yeah, it's not that easy.
Yeah, I think what you just said, Fernando, is a great point that a lot of these big questions probably aren't going to be answered immediately. Yeah, I think something that bothers me a little bit about the field is the way that we tend to have strong lines set up between old approaches and new approaches to doing things. And I think in practice, things work best when we have people who are working on building models and we have people working on critiquing those models. I think what we've seen the last few years with the sitter and KKLT has actually been a pretty healthy thing, combined with a lot of fights that probably weren't necessary. But a lot of really interesting new insights that have come out from that. And I think more generally, I think perhaps related to this, I think something that maybe we aren't doing enough as a field is I think there's a lot of really interesting work looking at these questions of, of course, de Sitter vacua, but more generally looking at things like the landscape, eternal inflation, these sorts of papers. There was a lot of really active work, a decade or so ago from people taking, I guess, the more non-swampland approach to string pheno is trying to construct these explicit models. I think there's a lot of interesting things there that it would behoove us to be better informed about. And I think that we can really make progress in looking at some of these claimed constructions and critiquing them and hopefully sharpening them with the more swampland style approach.
Right. Okay. Thank you, Tom. I fully agree with you. Okay. Miguel, you have been very quiet today.
Go ahead.
What can I say? Yeah, so I wanted to, going back on this line to, so what Ana with Ana Maria was saying, like we need like different directions to stabilize model or something. There's this very interesting work by Eva Silverstein and Bruno De Luca. They had a paper in 2021 where they are actually trying to stabilize moduli in a completely different way, right? They're basically trying to do a compactification on hyperbolic manifolds, is completely different from Calabi-Yau. And they want to use fluxes and curvature, but also Casimir energies. Now, the details of how all of that works it's complicated. Like they, as far as I understand, they don't have a very concrete example yet, but just the basic idea of trying to use quantum effects that we can control Casimir energies to, reliably find, potentials in very different corners of the landscape is something. I think there's a lot of. What I wanted to say is that I think there's a lot of progress that we can do, for instance, in that direction, right? These are, for instance, from this point of view, you can ask the question of, you have all the ingredients in principle to get things like the sitter, and you only have supergravity ingredients and quantum Euclidean curve space, and which are things that in principle we understand well enough to decisively, get answers. So yeah, I'm just wanted to highlight this way of thinking, like just more generally, like not perhaps just a particular paper, which is very nice, but the general idea of trying to use quantum effects like Casimir energies that we can control to either find the sitter or quintessence, or give perhaps more compelling evidence that it's not there in some point.
I fully agree. This is a good point. Yes, I have to say maybe one of the discussions I forgot to mention. Eva made a comment which I really like it. Because people say that we have been doing all this supersymmetry. She said, well, there are many things in physics that for which you can do calculations that you can trust without the need of supersymmetry. For example, all of physics. So essentially, we have to keep that in mind. So all of physics is not supersymmetric, and people have been able to do calculations. Yeah, that's a good point. The negative.
Wait a second. In that case, you can trust the results because there are experiments.
Sorry, I didn't hear.
So all of physics worked because then if you did some computations and then there was some experiment to double check it.
Well,
I think that's a crucial difference.
No, but it's also calculation that you can have. People.
Sure. I mean, you can be, but not. I mean, most of physics, let's say 99% of physics, was trusted because after an experiment, not before.
Absolutely. But I mean, the calculations.
That's our predicament. Well, I have the mic.
Okay.
So I have the feeling that we won't much progress until we understand the worksheet of the string in a Ramon background a little better, which is to say at all. Because right now, I mean, we have the P-spinor approach, but it's not, I mean, it's used for amplitudes sometimes, but we don't really, it would be good to have it as a tool to actually build the backyard that we can trust more strongly. Of course, that wouldn't be the solution to all our problems, but I think that would be. So young people go to the go west, go to the Ramon Field Center.
Very good. Very good. Fully agree.
The worksheet.
Irina.
Well,
yeah, also regarding how to make progress, I mean, I think, yeah, I really think we should try to make progress in formal string theory and many of these things, because sometimes it's the only way to answer the question. But the other possible avenues is also try to connect with other approaches. Like one of the things I like from the swamp is that you don't look only from top-down evidence from string theory, but you can try to connect with black hole physics. You can try to connect with people working in S-matrix bootstrap, people, I don't know, like working purely on CFT, like CFT techniques, like all of these developments about new types of symmetries, what maybe we can do with that. Like sometimes, I don't know, when we get blocked in one way, we can also try to open ourselves and explore all the other approaches and how to learn lessons from quantum gravity.
Very good, very good.
I think the message we heard from many of you is that we should explore all interesting possibilities and let 100 flowers blossom. Because last time somebody said it didn't go very well.
Okay, how are we doing with timing, Fernando? So what will we
can continue if there are more activity.
Okay, any suggestions? Any more? Okay,
David?
Yeah, just thought of something else. So you were presenting this needle in the haystack, and this is really my feeling as well, because since it's about cosmology, yeah, in the recent years we tried to make all our approaches on more better, more accurate, or under control. And whatever approach we took, it was always trying to get one model to work, which seemed to be extremely specific and not generic. So it's really about finding a needle in a haystack, which is getting a bit tiring. I don't know. I mean, the swampland was also promising to get general characterizations of what you can get, what you cannot get. And in the end, we are looking for something extremely generic, extremely non-generic. So I don't know what is the feeling of people on this, but this is also related to the comment on patience, because this is what we seem to need. But I don't know if somebody else has a better idea than looking for this needle.
Yeah, that's a good point, but I fully agree with you that we have to look for something non-generic, and that's the challenge. Just looking for generic things, that's not the way to go.
But concerning this needle, I just wanted to mention that, Fernando, you started with the first slide.
Yeah.
There were, like, if I remember, like 6 possible scenarios.
Oh, the second slide, yeah.
Or the second, sorry. And it's remarkable to me how our community focuses on almost one corner of all those possibilities. And I think we as the community move slow because we have all this technology and we like to keep on using the technology. But to me, as I said before, it's remarkable that I have not seen a paper that tries to connect ekpyrosis to the swampland, which I think is an obvious thing to do. How many of us are doing brain worlds? I think I don't understand. Like, the question, is Randall syndrome in the swampland, yes or no, is a question that I consider not to be answered. So I think there are lots of fun stuff to do. Absolutely. And the first papers in these topics are always the easy ones, so people should try it.
Absolutely. Well, thank you for the comment. Yeah, that's the reason I put all the different scenarios, like the pre-Big Bang on the string gas and so on. I'm sure if the swampland has something to say about the inflation, it has something to say about each of the scenarios, and it may not be that difficult to come up with some ideas. Like, remember, probably I'm old enough. I mean, what ekpyrosis was a big thing 20 years ago. It was there was only ekpyrosis and inflation. There were fights in every conference, and they had thousands of citations and so on. And suddenly people stopped worrying that much about them. But it is a valid proposal. Everything that has to do with the contracting universe, bounds universes. I mean, most of the proposals I mentioned, they have a bounds universe. So maybe someone has something to say about that. And I fully agree. That's good. Thank you.
I actually had a question about swampland and inflation. So I don't know exactly whether this is well established, but my understanding was that, this idea that inflation comes from some, effective scalar field flowing in some potential and so on and so forth. Is that idea contradicted by swampland arguments, or is it tolerated, or is it something which will be soon destroyed by swampland arguments? Or I'm not an expert, but I heard my understanding was that, this kind of idea of, some light scalar field rolling happily in a potential for 60 folds and so on and so forth was not compatible with some of the swampland arguments, but maybe somebody can clarify.
Very good, very good. I'm not the person to answer it, but I'm sure many people here can answer it. Irene?
Okay, let me try. Well, I don't think it's a question that can be answered with yes or no. It depends what model. With the swampland ideas, what we have realized is that things that you can try to engineer from bottom up cannot be realized, and like these parametrically large field ranges, and that's why we are trying to sharpen all these order one factors, all these ambiguities, to really be able to say how much you can travel in the field space without the EFT breaking down, and so on and so forth. So it is really it's a question of details. And I think at the moment there are, I mean, it's something in between. I mean, what we know for sure is that there are some models, I think, that cannot be realized. There are others that in principle there is nothing against if the field range is small. And then you can go to more refined things and try to constrain them. But I don't know, like from my perspective, it's not black or white. Like it's something between, which is also the interesting part, because then you can try to constrain and you can try to give some new information from top down about what things are more natural from a quantum gravity perspective and which ones are not allowed. But we need to sharpen everything first.
Absolutely. Okay, thank you very much. Okay, so I think that may be a good point. Oh, Marco, yes, please.
Yeah, I just want to add something about this. I think also depends a lot on the type of conjecture we are considering, because I mean, many times I hear of this, what this swampland allows, but I mean, we know that this swampland is made by a number of conjecture, and not all the conjecture might be true, right? So, for example, like if we take like the DS conjecture, I mean, this would not allow inflation. So, I mean, there are a conjecture that pose constraint on type of inflation. For example, the gravity conjecture pose constraint on the axionic type of inflation. I mean, the swampland design conjecture usually that would constrain on axionic models. Yeah, but I think that it depends a lot on the type of conjecture you take. And maybe related to this, I think is also like, given that again, that this session is called like swampland and Cosmo, to take really into account that most of the conjecture give parametric statements. And when we confront this, when we compare this with the cosmology, it is really important to determine the parameter of the conjecture that we're talking about. I mean, like saying just order one is not sufficient.
But if all conjectures are correct, does it rule out? I mean, let's say, in some ideal universe where all the conjectures are correct, for some reason, people got it 100% right. Is it going to rule out everything in inflation? I mean, because, okay, slow roll, you rule it by the de Sitter conjecture, and, a chaotic inflation, you rule it by the no super Planckian, by the field distance conjecture, and, you just rule out, can you rule out all of them? Is it possible that, if all this, let's suppose this whole program works and, for some reason, everything will turn out to be correct, in 5 years from now, is it going to rule out everything? All the inflation model. I mean, the idea of inflation itself, as some scalar field happily rolling in some potential or happily sitting at some positive.
So let me try to give a short answer. So slow roll single field inflation is ruled out in the scenario you give. Multi-field inflation might still be tried. Quintessence is borderline. That's the short answer.
Kunun is saying yes. So in the chat.
Okay.
I think this is a good place to stop.
Yeah, definitely. Okay, so thank you, everybody. Thank you for participations, and now enjoy the reception.